Bonjour, je voudrais parler en français aujourd'hui, mais je suis anglaise. Alors, I thank you for your patience and I respect your language skills and I will try to speak clearly in English. I'm here representing a manufacturer and I would like to tell you about our development journey and the applications that our equipment is used in, and I would particularly like to focus on some of the issues that have been raised already. So in terms of what AQMesh is, maybe you're aware of it. It is a small sensor system for stationary monitoring. It has both hardware and cloud processing system. And the ambition originally was to extend networks. So interesting question just now about community monitoring and so on. This was, the aim was to develop out from the compliance monitoring and improve the spatial resolution. So we've worked with Cambridge University, started measuring gases in 2011, which in terms of the speed of development is quite a long time ago. So we started using the AlphaSense gas sensors. We call version 3, that's our version that we released in 2013. The important point here is that we started collecting global data sets. Right from the beginning, AQMesh was being used all over the world, and this has been how we have developed our processing algorithms, so that we're constantly taking from various partners across the world comparison with reference, and I will talk a lot about the co-location comparisons, and this has been the fuel for our development. Initially, probably no surprise to anybody who's been looking at this, the biggest issues were the cross-gas effects, and certainly at that stage, NO2 and ozone were almost indistinguishable by the sensors, and the effect of temperature was very significant. So, the charts I'm showing you here are just to say that in the context of some very poor performance from the early AQMesh version, which was not good enough for many applications, even so, if I can, no, I won't try and point. The top row is showing the source apportionment from a reference station, left to right, NO, NO2, NOx, and the bottom row is AQMesh. And you can see, hopefully, that fundamentally the information is still in there, even with this very poor version. So we have users from this stage who have found that there is sort of worthwhile information. So key developments, the sun shield was introduced. I've talked about temperature sensitivity. It's still a significant issue. One small point I noticed from one of the photographs of AQMesh. AQMesh is involved in, I know of 3 independent studies in France this year. 2 have been mentioned so far. AQMesh was G in the study that we've seen. So happy to talk about any of those results. I got that right. So we developed the sun shield so that this has insulation and a reflective surface to try to minimize the impact of temperature on what is a sealed waterproof system. But in that case, I saw from the photo that the sun is shining on the back, which increases the temperature effects. So it's just a small detail about how there are issues about using this equipment, and when it comes to community monitoring, there is quite a lot of information and support we need to pass on. Similarly, I noticed there's a poster from Nilu, which shows AQMesh used in the CitySense project a few years ago. One point I would make is that we didn't characterize the sensors from AlphaSense. They went straight to the study. And there's a lot of variability. Well, there is variability between the sensors as they arrive with us. Maybe not as much as mentioned in the previous, the earlier presentation, but part of what we do now is to, I don't know what I'm doing with the microphone. Part of what we do is to put the sensors out in an ambient environment, co-located with reference, and we understand that variability before we start building them into equipment. So this is one of the processes that does add to our costs. So we still have significant temperature effects at that point. We were struggling to find the gas signal with these older versions of sensors. We tried artificial intelligence. I was at a conference in the US in September, a lot of talk about artificial intelligence. Our efforts did not go well. Artificial intelligence was very good at locking on to the temperature effects. So again, happy to talk about those experiences. So another previous version, version 4. In summary, we could get some good results, but we had variability. So sometimes we got an R-squared of 0.8 or more, but sometimes it was down at 0.5 or even lower. So local scaling was and continues to be important for AQMesh in terms of getting that improvement in accuracy, but it was critical with this earlier version. So, in terms of developments, we have an ozone-filtered sensor now for NO2, which has dealt with the cross-gas effect, and an improved response at higher temperatures. We do the factory check, and we have improved the setup at the very low levels, the very low gas levels. So, you can see the details on our website. But we are at the point now where if we see an R-squared below 0.8, we start looking to see what's going on. Was the co-location close enough? Was the pod the right way round? Were there any issues there? Did anything happen, at the server end? So we know that this performance is possible. And we are involved in co-locations all over the world, and sometimes between pods, sometimes pod to reference, also diffusion tubes. Sometimes we're told these two don't match. My best ever was when two pods were in, actually one was in Madrid and one in Barcelona. And, so very basic errors can be made in terms of if you're working on a server with serial numbers, but also just not getting the co-location quite close enough. And there are other issues which you're well aware of. So, in the absence of any process for certification, we look at data validity in terms of whether the pods read the same as each other, so the series of regression plots on the left, and also whether they read the same as reference. One point that was mentioned in terms of one of the studies was the very low gas levels. Now, we talk about a limit of confidence rather than a limit of detection. The sensors can detect the gas down to a very low level. So on the plot here, the line across is at 10 ppb, but you can see that there is a lot of information in the time series plot, even though the R-squared, the regression analysis, might be poor. So it is a relevant point there. And certainly the extent to which we expect that noise from environmental conditions, the electrochemical sensors like dry, particularly dry, cold conditions and hotter conditions are still more of a challenge. So I just threw this slide in, as I said, because I haven't heard much about it here, but in the US there was a lot of talk about different approaches with small sensors. So you can see how we do develop our single traceable algorithm, because when we sell a unit, it's very easy to ship, and they can be sold in one country and turn up elsewhere. So we have one algorithm which is applicable anywhere. So we don't use different algorithms. There is no doubt that if you focused on a particular area, you could do much better with your algorithms. We don't use training data sets, AI. We don't correct node to node out in the network, and we don't use remote calibration. So just those are a few points of clarification. I'm going to show you very quickly some production. This is our current version. We're moving on to version 5 now. But these examples are all on our website. I don't want to keep you from your lunch. The gist of it is that we are getting good results in a wide range of conditions. So that's in Minneapolis, it's cold. NO2, hot, humid, hot London summer. That's in industrial area in the States, hot and humid. Very important ozone in that area. Not quite sure where that is in Western Europe. Some of our partners prefer us to be more vague than others. But CO, our problem with CO is actually getting reference that can work at the same resolution as the sensors. So that's where it's harder sometimes to get comparisons. SO2, sometimes the R squared is lower, but if you actually look at the plot, the levels there, I think we're peaking at sort of 6, 7 ppb, very low levels of SO2. So we do now have CO2 and H2S. I won't linger on this, just to show we've compared H2S in a wastewater treatment plant. So for some applications, this is an interesting new electrochemical sensor option that we have. CO2 using NDIR, again, I'll talk about one of the projects that using CO2, and they're very excited about what it can add to the understanding of the environment. So our latest version of processing, we have improved the compensation for hotter conditions, and also if you don't have access to reference, the pre-scaled, or what we call the out-of-the-box accuracy, is improved. Likewise with ozone and CO. And also we can identify destabilization. So most of that is to do with human intervention. So for example, if you take a unit from an air-conditioned vehicle in Saudi Arabia and you put it straight onto a post, the electrochemical sensors are literally shocked by the experience. We can identify that through the raw output and withhold the information until we're confident that it's stable and it's legitimate. So these are the kind of processes we're building around now. So improvements in NO and NO2. As I said, this is all on our website, so I won't hold you up with that. I have talked most about gases, partly because we've been doing it for longer. We did introduce an optical particle counter in 2014. There's a picture there. It's very similar to the AlphaSense OPC, but one that was developed for us, and the mass estimates are calculated in much the same way. It has a pumped sample. The version that has been used in the studies is version 2, which is affected by moisture and deliquescence, and I'll show some plots of that. So what we've been able to do is filter out some of those, what we believe to be erroneous data points. And also the heated inlet was mentioned somewhere. We do offer a heated inlet. It comes at a price, though, of power autonomy. You can't run it off solar. So you do need a direct power source to have a heated inlet, but it does indeed deal with the problem of moisture very well. So one example of PM2.5 results, PM10, we're showing the scaled and pre-scaled there. But if you look at this plot, you can see that on the left, there's a variation. We're deviating from the reference there, and we think that is to do with moisture. But by taking out the data points, it is a filter. We're not compensating. We are simply removing data points with this version. We do believe we have a lot more that we can do in the development process with particles. We've probably focused a lot on gases over the last few years, but there's more to be done. And again, on PM10, you can see that very significantly, and you've got the humidity plot there to show that the left-hand side of the plot is affected by moisture, but by taking out points. It's a crude way of dealing with it, but it does. We have a lot of customers who are working on construction sites with alerts, and it's a problem for them if they have a false alert, effectively. So I've touched on it. The things that we're focusing on now are really about quality control, quality assurance. So what we manage at manufacture, we reject some sensors, we look at the sensor variation and the response, and we actually take that information and build it into our algorithms, and we do carry out scaling at factory. And when it comes to data delivery, we can take out data points which we don't have confidence in. So, for example, a sensor that fails, electrochemical sensors can fail due to extended high humidity, and we see the raw output change very dramatically. We immediately flag that on the server, we change it to a -998 flag, and we tell you the sensor has failed, we send out a warranty replacement. It is annoying. Somebody has to go to site and change the sensor, but what we try to do is manage that process as smoothly and affect the data as little as possible. So We do have a standard operating procedure, and we are working closely with authorities in the EU and the US to look at testing methodologies which allow users to understand the variation. What can these systems deliver? I think compliance is right at the bottom of the list in terms of what these sensors will be able to offer. So part of our user protocol is take one unit out of a group, put it against reference, compare, scale, and then move it around the network so you don't have to group all of the units at one place. Right, I'll push on. Right, used around the world, lots of countries, lots of conditions. So applications, transport monitoring, fairly obvious, includes before and after studies for developments, mitigation measures, how effective are they? We have one customer who's looking at different road surfaces and using AQMesh to measure there. Tunnels, very popular, but some of the levels in tunnels are so high that actually they sort of kick off a QA/QC alert because it looks like something's gone wrong. Monitoring around airports, very useful in terms of distinguishing pollution from traffic versus aircraft and so on. And we've done a lot around ports as well. And that's where CO2 is quite useful for if you want to look at SO2 levels, but are you looking at a plume from shipping? If you've got the CO2 level there to measure whether you've got combustion output, that's very helpful. Around cities, around communities, I'll mention one particular project which is relevant to that. Construction and industrial sites. I can talk, if anyone's interested, in a wide range of applications that the equipment's used in. The project I was going to mention is it's worth looking up Breathe London. This is a C40 project in London. There are 100 AQMesh units used in conjunction with the regulatory monitoring network and Google Cars. So the Google Cars are used to track around the city, potentially identify hotspots where the AQMesh pods can be moved if there isn't a reference station nearby. There's not much data coming out of that yet, but over the next few months there will be. But it's not the only place we have smart city applications in the US and the UK. The pod there was in a volcanic area in Nicaragua, sort of gently soaking in dilute sulfuric acid. It came back to us in a bit of a state, but had been measuring SO2 very effectively. A lot of good work done with modelling, using a larger number of monitoring points to improve modelling, using modelling to constrain perhaps the measurements from the monitoring points. And one study which is very interesting is this one done in Cambridge, where Professor Jones was able to distinguish between which pollution was coming from a local source where intervention is possible. This was important working with the City Council, and where the PM10 was actually showing the same readings right the way across the city. And the conclusion was that that came from a regional source, and local intervention was not possible. So there's a paper relating to that. It is quite interesting if you haven't seen it. Indoor, outdoor, AQMesh has been used in a study in London with a large office building where the heating and ventilating system has been managed very effectively by understanding different wind directions, different pollution levels at different inlets, and how that can be used. It's not a domestic, cheap solution, but it is starting to show what can be done with these sort of sensors. Employee exposure, we've talked about, and mobile. AQMesh is not designed to be a tool for mobile monitoring, but it has been used in a few studies. So what have we achieved and what is remaining? We think we've done reasonably well with the accuracy of gas readings. We think we can understand the limitations of these sensors, and we're happy to discuss those, engage, manage those limitations, and I've mentioned sensor failure. We have got better at offering better accuracy without the local scaling. Not everybody has local reference, not all applications. The example in the previous presentation illustrated that. We're trying to make a practical monitoring tool, and I think some of the tests have highlighted how significant those practical issues are. And we have got equipment used around the world, which does bring challenges. So we can't see when a pod has been moved or destabilized, and we need to try to use the opportunities from our smart and remote access to the hardware to manage that. So there's more to come around QA/QC. Very happy to discuss that with anybody here. And as I said, there's a certain amount of tension between professionals using this kind of equipment to extend networks and happy to follow standard operating procedures and what you might expect community monitoring project to need. So more remote diagnostics and improved QA/QC, and we think that we can measure, we can provide useful information to a lot of applications now, and certainly we have customers who are using the equipment and making repeat purchases and so on, but we do want to engage the whole issue of data validity. We're very happy to have that discussion. And any questions?
Thank you for your presentation, very interesting. Sorry, I'm here. No problem. I was quite surprised by one of your comments saying that for compliance purposes, these sensors are really, well, it's the last thing you want to focus on. Can you explain and tell a little bit more why you don't think compliance is already possible with these results?
Required in terms of uncertainty for reference or compliance monitoring are well established, and there are methodologies, and in different authorities, you know, the US, it's actually fixed by law, the methodology that must be used for compliance. The opportunity we see now is to fill in the gaps with the compliance, and it is the authorities that have the curiosity and trying to understand what's going on behind that is useful. We're not saying that we can't get to compliance, but we think it's a missed opportunity to just focus entirely on that. I think we will get better, and the methodologies and the standards, I hope, will move in a way which is practical and allows this sort of equipment to be used effectively. But right now, those standards are really not designed for this sort of technology, and we think we have things we can offer in the meantime.
Sorry, I got two questions. First was about the public price and a rough range of that. And the second is a little bit more technical. You mentioned earlier that you had to filter the NO2 against the ozone sensor because it was both interfering. Did you have the same way for the ozone on the NO2, or is the NO2 correct enough to be standalone?
Yeah, the filter... I have seen some products using the same sensors filtering in the opposite direction. The filter is on the NO2 sensor. Basically, we still have to do the cross-gas correction. So we still, if you want to use this equipment to just measure ozone, you have to have an NO2 sensor as well, so that you can correct for that. But we now believe that the correction is possible, and indeed the results we get for ozone are very good, whereas in the past, and we were having to do things like, you know, massive averaging and smoothing to get meaningful results, whereas the results we get now, I'm happy to share, for example, the results from the US where there's a big focus. But yeah, we think we're there with that now. The public price? Range about 5,000 to 10,000 euros per unit, and that's talking about particles, all the gases, and the extras. You've seen how much development we've put in, and we're nowhere close to paying that back. And you've seen the studies we're involved in. What we hope is that our ambition of having large networks will be realised, and then everything scales. and the costs scale too at that point.
Thanks for presentation. Do you share with, is it possible to share the data that you collect all over the world? Is it a cloud where we can use it for modeling, for example?
The plots are available. Make contact with me because it depends on the partner, and also things change over time. So maybe data was collected a few years ago, now it's not so sensitive, the city authorities have seen it and they're happy for it to be released. So it depends. I'm happy to put you in touch with owners of data and see if they're happy to share.
Hello, I have a technical question. You showed me that you show the pre-scale and scale data. And what is the methodology behind how you get your scale data?
This is where we co-locate with reference. So pre-scaled is as the data comes out of our algorithm, and then a scaled is where you do a regression comparison, you have slope offset, you apply that to the data. That's scaled data.
And what is the reference?
The reference?
Yes, the reference devices you use.
Well, these are the EU methodologies, so whether it's chemiluminescence or, as approved.
No. Is it local, from local sources, or you use from other sources?
Local is best. So ideally, if you want to measure in Lille, you find a reference station in Lille and you do your co-location, slope, offset, and scale. And then you can move the equipment around. Ideally, at the end of your project, you bring the equipment back, the AQMesh pods, and you just confirm that nothing's changed and they still compare well.
Okay, thank you.
Et donc, le colloque reprend à 14h30. Et juste après, donc, la pause déjeuner, qui est, je suppose, dans le hall. Merci.